start.
Okay.
And again, guys, for those of you sitting near that, just make sure if it is off, just let me know. We can restart. Okay. So, chapter 1, Introduction to Organic Chemistry, and the second half of this chapter, we're going to study the first class of organic compounds called alkanes. Okay, so it's 2 parts. So first, let's take a look. What is organic chemistry? Okay, what is organic chemistry? Here. Now, organic chemistry is much newer than other types of chemistry. Until, you can see that until 1828 is the mark of the start of this concept of organic chemistry. This whole concept, this organic concept, started with this reaction. But before that, people thought, or people assumed, organic transformations can only happen within living organisms. Okay, that's why the word coming from, so organic, relating to living kind of. They believed organic compound can only be from another organic compound within a living entity. Until 1828, a German scientist, he accidentally, when he started to heat this inorganic compound called ammonium cyanide in a flask, not in the living organ, and then he converted this compound into an organic compound called urea. Have you guys heard of this, the urea? Yes. Okay, you guys pee. This is one of the major nitrogen containing compound in your pee, your urine. Okay, and this one can also sometimes, if you guys have hard skins, you can the doctor can prescribe you to soften the hard skin on your hand or on your feet. It's actually prescribed to use prescription. But this is the first time ever human knowingly synthesized organic compound in a flask from any inorganic source. So that totally break up what people used to think, hey, organic must from another organic. They call it vital force. And that marked the invention of, or the start of, organic chemistry. And this guy actually realized, he said, I must have something big. I hit something big. He wrote a letter to his colleague. He said, I found like what? I found a primeval tropical forest. He thought he discovered something big. I mean, that's amazing. I mean, he only did one reaction, so he did something big. He was right. Organic chemistry is a huge area of everything. Okay, but that's the beginning of what organic chemistry means. Okay, now, if you look at this pie chart, I don't know when this pie chart was made. Probably still need to be updated by now. But you can take a look. The number of compounds comparing between inorganic and organic compounds. You can see what's the difference. There are more than 10 million organic compounds compared to 1.7 million inorganic compounds. Right? There's more than. That's why that guy said he discovered something, a forest. Okay, there's a lot more than organic compounds than inorganic. So we want to first know why. Okay, why there are so many, and why I said the pie chart needs to be updated. Why the number of organic compounds are almost limitless. Okay, their number is increasing. New ones are discovered and synthesized daily in the labs. Okay, why is that? Okay, first, what is organic chemistry? What do we study? Okay, in order to answer this question, we want to know what are we studying in organic chemistry? Okay, organic chemistry is the study of carbon-containing compounds. All organic chemistry are built on an element called carbon. At least in this planet, on this planet Earth. All living things, organic compounds, are built on carbon. Okay, this picture shows you if you burn your up, take away any other elements, what we left up is we left a bunch of carbon. We're built on carbons. So organic chemistry is the study of what? Carbon-containing compounds. okay, carbon-containing compounds. And we also should say almost all compounds that contains carbon are what? Organic compounds. There are some exceptions like these guys. Okay, these are tiny small ones. For example, carbon dioxide, carbon monoxide, element carbon such as diamond graphite, or these calcium carbonate, these small inorganic salts, oxides. Other than that, a little more complex organic compounds, as long as a little more, maybe contain 2 or more, 3 more carbons compounds, mostly are what? Organic. These are some exceptions. They're simple inorganic. Okay? Quick concept. Ask you. See, this is how you were asking. I won't ask you, hey, can you give me a definition of organic compounds? That's silly, right? Nobody would do that. But can you answer the question? Which one of the following is an example of organic compound? Which one?
D.
D. Why D?
Because it has carbon.
Because carbon is what? It looks more what? The formula like 2 carbons and 6 hydrogens is more what? Complicated. You can think she's right? Yes? Come on. Yes, the answer is D. Okay, answer is D. E and A, they both are carbon containing, but they're not organic. They're just simple inorganic compound. E is a carbon monoxide. It's a simple carbon oxide. A is inorganic salt, sodium bicarbonate. Okay, it's baking soda. Okay, so you don't even consider B and what? C, because they're not carbon containing. Okay, so next I want to give you a few examples. Okay, showing you some organic compounds you may have heard or definitely have heard. And I will show you what I meant by organic compounds are built on what, guys? Carbon. Okay, these are some models. Okay, the black balls are carbons. Okay, you can see carbon basically built on what? The whole backbone of organic compounds. The left molecule is a single sugar called glucose. We have a lot of glucose in your blood. Okay, for diabetes patients, they test their blood sugar. They're testing this guy, glucose. You can see that glucose is 6 carbons. They make a ring with the oxygen, and 1 carbon is outside the ring. That's glucose. And when glucose link together, this is a part of it, will make a huge molecule called cellulose. What is cellulose? Trees, grass, anything you see outside the window, covered the whole planet is this guy, cellulose. Okay, that's the end product of photosynthesis. Plants use solar energy, synthesize glucose. Glucose make that's how they grow. Okay, that's the main part of the cell wall of plants. Okay, and this one is cholesterol. Okay, you can see that is big molecule. Again, these are all carbons. Okay, cholesterol, you guys heard of that? This is sometimes related to what? Related to heart attack, heart diseases. Okay, the whole image, society news give it a bad image of this molecule. Okay, it's like you shouldn't take any much from your diet. But we're going to learn in chapter 8 what is cholesterol. Okay, what is cholesterol? Cholesterol is actually one of the most important stereolipid in our cells. We have a lot of them. Okay, it's not like you shouldn't. We need a lot of them. Okay, next. No. Okay, that's all. Okay, but again, I want to give you examples showing you organic compounds are built on what? Carbons. Okay, built on carbons. So next, why carbons? Okay, how carbon is used as the network builder to construct organic compounds. Okay, what makes carbon special, and how does carbon bound to other atoms or bound to each other? Again, we said carbon is the backbone. Right? You build on your backbone, you're adding on meat and skins, you make a whole entity. We're built on carbon too. Okay, we're carbon based. Some aliens may be other based, but we're carbon based. On the whole planet, we're all carbon based. Okay, so what is so special with carbon? Okay, carbon has 6 electrons. Okay, 6 electrons. Out of those 6 electrons, 4 of them are in the outer part, like these 4. Okay, the arrows represent electrons. 4 of those electrons are on the outer shell of carbon. They are responsible for bonding. Okay, we're responsible for bonding. However, among these 4 electrons, only 2 of them are single. You can see they're single electrons. So technically speaking, only these 2 electrons, these 2 are paired already. You can see that these are how carbon electrons are arranged. These 2 electrons in these 2 orbitals, only these 2 can be used for bonding with other atoms. So if carbon bound like this, each carbon can only make 2 bonds. Which, if that's the case, there's no way you can make complex organic compounds. Think about, if carbon can only make 2 bonds, what happens? Carbon can only make a what? Like a string, right? Think about, if something can only make 2 bonds, what happens? You can only make a necklace, right? You can never make a complex organic compounds, or even not even a living entity. So what happened is these 4 orbitals holding these electrons, again, only these 4 will be responsible for bonding. They mix together. Okay, these 4 orbitals mix together. They make 4 new ones. And we call that mixed process hybridization. Okay, hybridization. And they mix together, make 4 new ones. And in each one of these 4 new ones, now it has what? A single one. Okay, 4 new ones, each one holds a what? A single electron. Remember, if you want to make a bond, you need a single electrons, not a single electron to make a bond. Otherwise, you cannot make a covalent bond. And we call this process hybridization. Okay, hybridization, basically a mixed process. And then we call this type of hybridized orbitals sp3. Okay, sp3. What is this sp3? Where does it come from? Take a look here. It used one of this s and 3 of those p's. So together is sp what? 3. S, this is the s. P, this is the p. But how many p's here? 3 of those. That's why you got an sp3. Does it make sense, guys? And those 4 now are equivalent. They're almost identical, except they point different ways. But each one, again, points where? Each one, again, holds how many electrons? 1 single electron. Okay, once carbon does that, carbon look like this. The ball is the carbon. These 4 sticks holding 1 single electron. These 4 sticks are 4 sp3 orbitals. You can see that? And this is what a carbon look like in organic chemistry. We call this geometry, these 4, you can see that they're pointing the 3-dimensional. We call this geometry tetrahedral. Tetrahedral. You guys see that? You can, by the way, you can buy a model from Amazon, like 20 some bucks. It will help you to view the molecule. Okay, now we have 4 orbitals. Each one has, again, how many electrons? 1. And this is called sp3, hybridized carbon. Okay, it's hybridized already. It's ready to bond. And it looks like this, the same. Okay, the carbon is here, 4, showing like this. This geometry, this shape is called tetrahedral. Okay, it's from. Okay, and after that, like I said, carbon is ready to bond. Okay, carbon is ready to bond. If carbon use that single electron, again, this is called what, guys? sp3, one of them, bonded with a hydrogen. Hydrogen has 1 bond, 1 electron as well. So when they get close, now they make a what? CH bond. You guys see that? This contains how many electrons now? 2. One from sp3, another one from what? Hydrogen. Now we're making a bond. And you can do that 3 times. Okay, make another 3 more times, make another bond with hydrogen, make another bond with hydrogen, and make another bond with hydrogen. Now you have your simplest organic compound, CH4. You guys see that? Still tetrahedral. Why? Because these 4 orbitals are already tetrahedral. They're just making 4 bonds. And this is what the molecule looks like. You guys see that? We call this methane. What is methane? If you guys use gas at your home for cooking, some of you use gas for heating This is the gas you're burning every day. Methane, natural gas. Does it make sense? And this type of bond, okay, this type of bond, you can make a note here, is called a sigma bond. Okay, this type of bond is called a sigma bond. Okay, they're approaching each other like this, called a sigma bond. Does it make sense, guys? One electron here, another electron here, hydrogen has an electron. So when they approach, they make a bond. Paired, electron now is paired. They make a bond. And the same. Does it make sense, guys? This is how carbon bonds with other atoms. Okay, again, very important information. You don't have to know the details. Okay, I know some of you never will understand the details. It's fine, but you need to know carbons in organic compounds are what? sp3 hybridized. Okay, sp3 hybridized. And those 4 orbitals are called sp3 orbitals. Each orbital contains what? One single electron. And the geometry of the sp3 carbon is called what? Tetrahedral. And as long as you know what it looks like, it's fine. Good. And then, of course, you can make a bond now. Because single, they can pair and make a bond. Okay? That's for methane. Of course, carbon doesn't have to bind with hydrogen all. Carbon can bond with what? With another carbon. You see that? Imagine this carbon will also have what? Will also have sp3 orbitals. For example, this is one of the sp3 of another carbon. This is one of the sp3 for one carbon. They can what? They can make a bond. See? That's how carbon what? Bond together. Do you guys see that? You can make another bond carbon here and another bond carbon. And of course, the other parts you can put another carbon or put a hydrogen. And that's how we have a lot of molecules like this. Okay, so far we have only talked about carbon and hydrogen, of course. Do you guys see that? This is how methane looks like. This is 2 carbons bond together. The rest of spot has what? Hydrogen on it. This is 5 carbons bonded together, and you have hydrogen on the rest spot. Does it make sense? But each carbon, take a look, has how many bonds? Each carbon has how many bonds? 4 bonds. Do you see that? Right? 4 sp3. So it has to make how many bonds? 4 bonds. No matter you're bonding with a carbon or bonded with hydrogen, total has to be how many? 4. Because carbon looks like this. That's 4 bonds. Does it make sense, guys? Each carbon will always have what? 4 bonds. No matter you're bonding with hydrogen or carbons, total. Okay, take a look. If I bond with 2 carbons, the carbon will look like this. 2 carbons and 2 hydrogens. You guys see that? Of course, these 2 carbons can have more. If you look at this carbon only, how many bonds? 4 bonds, right? 1, 2, and what? 3, 4. And the same, if you look at this carbon, there has to be other bonds bonding too. Can be other atoms too, can be oxygen. Doesn't matter. But if you look at a single carbon, there must be 4 bonds on it. Does it make sense? Okay, sp3, because you have 4 sp3 orbitals. Okay, so that's part of the reason why we have what? So many organic compounds. Because carbon can technically build what? As much as you want. They cannot build it. They don't have to build one at another. They can build what? Branches as much as you want. This is like a line, but they can build as much as they want. That's part of the reason why we have so many organic compounds. Because there's so many ways of what? Nature can build with carbon. Okay? Quick summary. So far we have learned. Carbon always have how many bonds? 4 bonds. Okay, 4 bonds. Hydrogen, on the other hand, because hydrogen only have 1 electron, hydrogen can only have how many bonds? 1. Hydrogen is always at the terminal. If there's hydrogen here, there's nothing else. Why? Because hydrogen only have 1 electron. There's no way for hydrogen to bond to anybody else. Does it make sense? So far we have learned these 2. We'll see the others later, don't worry. Okay. Number of bonds for hydrogen, how many? 1. Number of bonds for carbon, how many? 4. And there's number of bonds for oxygen and nitrogen as well. Again, we'll study later. Quick. Is this structure, does this structure look correct to you? Regarding the number of bonds, take a look. You're shaking your head. Which one is not correct?
The nitrogen.
The nitrogen has how many bonds?
3.
3? Does it have 3 bonds on nitrogen? Yes. Right? Anybody? Can I find a mistake in the structure? Of course, this is 2-dimensional, right? We're not putting 3-dimensional, but do you see correct number of bonds for all the atoms shown here?
Carbon only has 2, right?
Which one? Which carbon? There are 3 carbons here.
Oh, 3. Mhm.
Which one has 2 bonds?
Oh, wait, never mind, got it.
All correct? Yes, this is correct structure. Okay, carbon has 4 bonds, hydrogen has 1 bond, nitrogen has 3 bonds, oxygen has what? 2 bonds. Does it make sense, guys? Again, we'll study the oxygen, nitrogen in later chapters. So far, in the first chapter, we only worry about carbon and hydrogen. Does it make sense? Okay. Next. Not that bad, right? Because that you will forget everything when you go home. That's why you need 4 hours after. Okay. Now, because there are so many organic compounds, there's no way we can study them one by one, right? It takes forever. Nobody does that. So, how do we study organic chemistry? Organic compounds can only be studied by categories, by types of compound, by classes of compounds. Just like you go to grocery, you shop for what? Cereal, you shop for dairy, you shop for drinks, right? There's no way you do one at a time. You just by groups, you organize these by groups. The same for organic chemistry. So, organic compounds are studied by classes. And how do we divide them into different classes? We use a group of atoms on that particular organic compounds. We call those groups functional groups. Some organic compounds have a certain numbers, certain few atoms, they make a group. And this group will distinguish one type of compound from another. For example, okay, some compounds have this guy, oxygen and hydrogen. And those 2 atoms is a group. So anything that contains this group, O and H, is called an alcohol. So no matter how small or how big the molecules are, they are what? Alcohol. And they will have the chemical property and physical properties of alcohols. That's how we study them. Does it make sense, guys? We don't study individual compounds. We study them by what? By groups. Okay, by groups. Or, if we don't talk about the nitrogen and oxygen, we look at the carbon and hydrogen as well. Some organic compounds have this carbon-carbon double bond. And we call those organic compounds alkenes. No matter they're small or big, they're all alkenes. We study them all together. We'll study that in chapter 2. Does it make sense? So, organic compounds, again, are classified by what? By their functional groups. Okay, we will study most of them in this picture. Okay, we'll study most of them. In the first 6 chapters, we're basically studying these functional groups. Okay, except for chapter 1. The compounds we're going to study in this chapter, technically speaking, they don't have any functional groups. If they don't have any, they're still a class of molecules. Okay, starting from chapter 2, they will start to have these functional groups. Does it make sense, guys? That's how we study organic compounds, organic molecules, by classes, by functional groups. Okay, functional groups, again, are what? Small group of atoms that distinguish one compound from another. That give those compounds a what? A unique property. Chemistry property or physical property. Does it make sense, guys? Again, you can interrupt me anytime if you want a question, if you want to clarify some concepts. Okay, now, in the first 2 chapters, we're going to study organic compounds containing only 2 elements. In the first 2 chapters, chapter 1 and 2, we're going to study organic compounds containing only 2 elements. That's our what? Carbon and hydrogen. And we call those compounds hydrocarbons. Okay, hydrocarbons. You can see that the name, based on what the name, you know what they're composed of, right? Hydro means what? Hydrogen, carbon means what? Carbon. So in their formula, no matter molecular formula or later on we're going to study structural formula, you don't see anything. You don't see oxygen, you don't see nitrogen. You only see what? CNH. And of course the CNH can be C2H6, C5H12, C5H10, can be all kinds of numbers. But you only have what? CNH. Okay, N and M are subscripts, are whole numbers, indicating how many C's, how many H's. Does it make sense, guys? Those are our targets for the first 2 chapters. We call those molecules what? Hydrocarbons. What are hydrocarbons? Anything with a formula like this are hydrocarbons. Does it make sense? Okay, those are first 2 chapters. In the first chapter, we're going to study hydrocarbons with owning CC single bonds. Okay, carbon and carbon are bonded together with like this single bond. One bond. Single, single, single. You can see that? If a hydrocarbon, again, we're talking about hydrocarbon first of all. If a hydrocarbon contains owning CC single bond, okay, single bond, then we call those hydrocarbons alkanes or saturated hydrocarbons. Okay, saturated hydrocarbon means alkanes. Alkanes are saturated hydrocarbons. Does it make sense, guys? This is what we're going to study the second half of this chapter. And we actually started already. In chapter 2, we're going to study hydrocarbons with CC multiple bonds. Multiple means what? Double, triple, or something like this. We call those hydrocarbons unsaturated hydrocarbons. That's what we're going to study in chapter 2. Does it make sense? That's how we classify hydrocarbons basically now. Hydrocarbons can be classified into what? 2 types. Is that right, guys? First type with CC what? Single bond only. You don't say anything else. All single bonds. Of course, CH is always single bond. Why? Because hydrogen only has 1 bond. You don't have to worry about the H. If you only see single bond, CC single bond, those are saturated, and we call them what? Alkanes. Okay, alkanes. If they contain multiple bonds, we call those what? Unsaturated, and we'll study them one at a time. Okay, in chapter 2. Okay, they're in chapter 2. Does it make sense, guys? So far good? Easy, right? Okay, next. Let's take a look at alkanes. Like I said, we only study what? Alkanes in this chapter. What are alkanes, guys, again? Hydrocarbons containing only what? Single bonds. They're called saturated as well, but we call them alkanes most of the time. Okay. Alkanes can be represented using a general formula. CnH2n plus 2. CnH2n plus. What does it mean? It means if I know the number of C, n means what? Whole numbers. There's no fractions. In the formula, there's never fractions. If I know the number of n from 1 to what? A million, you call it. I can calculate the number of what? Hydrogen. Using the math. 2 times n plus what?
2.
Plus 2. If n equals to 1, H equals to 2.
Yes. 2 plus
2 times n plus
4.
2. 4. Okay, so CH4 is the first one. It's the simplest one. We just built it, right? CH4, guys. If n equals to 2, H equals to 6. Okay, guys, you have to do this in your mind. You don't have people to tell you how many H. You know it. As long as it's what? As long as people tell you it's what? Okay. C2H6. Okay, it's called ethane. Okay, we do have a tiny amount of ethane in your natural gas, but most of it is this guy, CH4, in your natural gas. If C equals to 3, H equals to 8. 3 times 2 plus 2 is 8. And the molecule is called propane. Okay, you guys know what propane is, right? You get propane tank all the time. What's in that tank is this guy, C3H8. Okay, you're burning that in your July the 4th, Memorial Day. When carbon number equals to 4, H equals to 10. Okay, the molecule is called butane. Okay, called butane. What is butane? The lighter gas. Liquid is called butane. It's pressurized. Butane is a gas, in fact. If you open the lighter without lighting it, you can see the seasoning, right? That sound is from butane gas. Okay, there's something called what? Mother eats peanut butter. So methane, ethane, propane, butane. It makes sense? How you memorize the names? You will have to. Okay, mother eats peanut butter. MEPB. Methane, ethane, propane, and what? Butane. Do you guys know something, a trend? What's similar between these four names?
A.
They all end with what? A-N-E. Do you guys see that? Why they're all ended with A? Because they're what? Alkanes. Okay, alkanes. Okay, keep a side note. We'll study them. Again, you have to memorize those names. There's no way I can help you memorize the names. I can give you some help, the trend showing you. They're all alkanes. So their name will always end with what? A-N-E. So what's the difference between their names? It's the prefixes. Meth stands for what? 1. Eth stands for what? 2. Those prefixes tell you the number. What number? Number of carbons. Prop is what? 3. B-U-T is what? 4. There we go. Okay, keep that in mind. Again, we will study them all together. Okay? Quick question, guys. Which one of the following is alkene?
B.
B?
E.
E, B, which one?
E.
E, why? Because it matches what? CnH2n plus 2. See, guys? I will never ask you to write down like a, hey, can you tell me the formula? This is how I'm going to ask you. Does it make sense? Okay, first, alkane, what? You don't need to worry about A and C. Why? Because they have oxygen. Alkanes only what? Have carbon and hydrogen because they're hydrocarbons. And alkanes, their formula must match what? CnH2n plus 2. Only C5H12. By the way, the name is pentane. Okay, name is pentane. C5, the prefix is P, P and T. Like a pentagon. Pentane. All right, move next. In organic chemistry, only by knowing the C something H something is 1% of the job. Because that doesn't tell you what the molecule look like at all. Why we're talking holding a model? Because it's more important in organic compounds is not they're composed of, right? All hydrocarbons is C and H. Done. They tell you nothing. They tell us nothing. Organic compound, as a matter of fact, you notice already only contains what? A few elements, right? We're never use the periodic table. Why? Because we only look at the CH and N and N and O and sulfur and phosphorus. That's it. We don't have much element to study. What matters for organic compound is what? What it look like, the structure. The structure. So we have to know how do we represent the structures of organic compounds. There are a few ways of showing their structures. One way is to show the element, of course, and how they're bonded together. So every single bond you show them, like this guy. Do you see that? Every carbon and every hydrogen, and we know carbon and hydrogen bonded with a single bond, so we show everything. We call this structure, of course, the structural formula, but we call that expanded structural formula. Expanded means what? We basically showed everything. How carbon is bonded to another carbon, how carbon is bonded to how many hydrogens, etc., everything. This is great, right? Shows you everything. However, there's one problem with it. For small molecules like this, you can do it, even though it's ugly. If for a bigger molecule, imagine you have a prescription. Your drug have a label, and your drug normally have a structure. There's no way you can put it a structure with like that. It will cover a whole page of paper. So we have to simplify for somehow. We have to abbreviate the structure, make it easier. And that's how we end up with a condensed structure. Okay. What is a condensed structure? A condensed structure is you still show the atoms, show the elements, show the atoms, but you don't show CC or CH single bond. Okay, I repeat. You still show C and H, but you don't show the single bonds. You know the bonds are there, you just don't show them. So we just take all the bonds away. So the molecule like this will become here. Can you see that? Can you see these two structures are the same? This first C has how many hydrogen on it? 3. So it's what? CH3. Do you see that? There's 3 bonds together. We just don't show them. We know they're there. The second C has how many hydrogen on it? 2. So CH2. Right? And of course, this C is bonded with that C. Even though the hydrogen between them, they're bonded. We know hydrogen can never be between anybody. Hydrogen can only be what? At the terminal. So you know they're there. We just don't show them. And the same CH2, CH2, and what? CH3. You can even make it more condensed. I mean, not necessary, but sometimes useful if the chain is too long. We can put a parenthesis, put a 3, means there are 3 of what? CH2s. That works too. See, that's much prettier, right? It doesn't look as complicated as that. We don't show the single bond. That's one way of showing organic structures, condensed structure. Okay, maybe 40% of the time we use this structure. And you can use it too. Another, even more condensed structural formula is called skeletal structure. In skeletal structure, we only show the skeleton, how they're bonded. We don't show anything. We don't show C, we don't show H. We only show C how they're bonded to each other. This is the skeletal structure of this molecule. In a skeletal structure, you can see there are zigzag lines, right? Each end, there has to be an end. Or each angle, you can, a corner angle, whatever you call it, angle, beginning, end, represent a what? Carbon. Remember, we're built on carbon. The backbone is carbon. So these are all what? Carbons. And of course, this carbon is bonded to another carbon. This carbon is bonded to these 2 carbon. That carbon is bonded to these 2 carbon. That carbon, etc. Does it make sense? Okay, that's a carbon. And we don't show anything. We don't show hydrogen at all. But you may ask, hey, how do I know? If I look at a carbon, how do I know how many hydrogens do we have? Okay, there's a very easy way for you guys to figure out. And once you're like me, if you draw a lot of organic compounds, you don't need to like rethink. But for you guys, there's one very easy and reliable way. Just look at that carbon. For example, look at this carbon. How many bonds do you see? 2, is that right? You see 2 bonds? Those are 2 bonds with what? Carbon. Total carbon should have how many bonds? 4. So how many you don't see? 2. Those 2 are what? Hydrogen. That's why this carbon is a what? CH2. Does it make sense? You ask yourself, how many bonds can I see? Those are the bonds with carbon. The one you don't see are what? Hydrogens. Hydrogens like a fillers, right? You have to make up all the 4 bonds. Does it make sense? The terminal one, how many bonds do you see? 1. That means how many you don't see? 3. It has to be a CH3. Okay. In this class, or in the future, you see organic compounds, you don't see those type of structures. You only see either condensed or what? Skeletal. When you draw, you can draw these 2, either one. But I will probably draw 60 to 70% is use skeletal. Okay, you have to get yourself used to skeletal structures. Okay, I'll show you more. Okay, give you a few minutes, take a look. Do you understand? The expanded structure can be translated to skeletal. Take a look. You see that? 4 carbons. Is that right? So you do a zigzag what? Until you see 4 ends and angles. Total is what? 4. So 1, 2, 3, 4. You do zigzag. Okay, I'll show you later why we do zigzag. Okay, I'll show you with the model. 4 carbons, CH3, CH2, CH2, CH3, C4H10. You don't need to count. 4 carbon, 10 hydrogens. If not, something's wrong. Here, how many carbons? 4. See that? There's a carbon in the center, so I put 3 lines here. So 3 lines here. You see that? And the center carbon has what? 3 bonds. So how many hydrogens? 1. See that? 1 hydrogen. See that? Again, now you make sure you know this makes sense. And after that, you have to practice. Okay, changing them back and forth. Somebody say, I don't know where to practice. These are your practice. When you go home, cover it, right? Try it by yourself and then see if you did right or not. Like I said, if you get yourself 100% familiar with the lecture notes and the quizzes, you will find yourself the best in class already. Okay, somebody, I don't know how to study. If I say something on the lecture, you know, hey, I know what you're talking about. I know how to do that. You can do it like this. You're good. I'm not asking you to read 2 books. Okay? More here. This one is the expanded, of course, using model show you. Okay, and also the condensed, the skeletal. Take a look. Again, you need to make sure it makes sense. If not, ask me. Come on. Give you a couple minutes. Okay, now I'm going to show you why it's zigzag. Again, if it doesn't make sense, please let me know. I'll explain. Okay, this is the connection of 4 carbons. Do you see that? Why we zigzag? That's how carbons are bonded. Why carbon binding like a zigzag? Because carbon is what? What's the geometry called? Tetrahedral. It has to be like that. You see that? This is 4 carbons. 3 carbons are like 5 carbons. You always keep it. That's why doing zigzag represent the most stable conformation. Later on, we're going to talk about of organic molecules. Okay, we show the backbone. Basically, we're showing what? The backbone. People know it's carbon because we're built on carbon. We don't need to show carbon. Okay, this whole thing is built on carbon. Make sense, guys? These structures? Okay? I'll give you a quick practice. Okay, quick practice. This is yours. Do it at home. Do this one. Translate these 2. Okay, translate these 2 into skeletal structure. The top one you do at home. Okay, translate these 2 into skeletal structure. The bottom 2, okay, translate that into skeletal. Okay, into skeletal.
So with the second one, you have to show the double bonds with
Yes, yes, show the double ones. Don't worry, I can show you later. Okay, translate the bottom 2 structures into skeletal structure. I'll try to build a model for you. The second one is hard, it's fine if you can't do it, but the first one you should be able to do it. Anybody done? Want to show me the first one? You got the wrong note.
No, I know. I know.
Okay. That's not for my class.
No, this is chemistry.
Yes, but those are from Dr. Burke's class. Yes, that's not from me.
Okay.
That's from me.
Okay. So that's the first one. That's the second one.
Almost correct. Second one is missing a carbon. You see that one
Yes.
outside the ring. Yes, that's correct. Very good. You got it? No. All right, let me show you guys. The first one, how many carbons?
4.
How many carbons total? 5. There's 1 carbon, what? 4 carbons of what? Bond to it, right? So 1 carbon, 4 carbon bonded is what? It's a cross. You guys see that? 1 carbon. Again, we don't show carbon. Every corner end interception is always a what? Carbon. And there are 4 carbon bond to it. Just draw 4 carbon bond to it. Done. You see that? This one has a what? Has a ring. Do you guys see that? Again, don't worry about what the molecule is. We'll study them later. Ring has how many carbons? 6 carbons. So you need to draw a what? Draw a ring with 6 carbons. You see the ring? Like hexagon, right? 6 carbons, 6 carbons. You're basically representing the same thing, except you don't show the carbon. Do you guys see that? And then there are 3 double bonds alternating. Double, single, double, like this. Make sense? You guys see that? Again, a hexagon ring with double, single, double, single, double, single. So double, single, double, single, double, single. Do you guys see that? And then there's a carbon here. Do you guys see that? Outside the ring, so I put a carbon outside the ring. Does it make sense? That's how you convert a structure what? To skeletal. It's more difficult than convert skeletal to expanded. You just draw some. That's why I ask you to just draw it at home. You can do it. Okay, make sure you do it. Okay, I have a quick question for you guys. Look at this molecule here. It's a ring. How many carbons do you think there is? 6 carbons. Now, don't do the formula. This is not the same we talk about. Can you count how many hydrogen? Count. How many hydrogen? 6 carbons, correct, because it's hexagon. 6 carbons. How many hydrogen do you think there is?
6.
How many? 14. Huh? 14. I'll say 14. No? 12 carbon and 12 hydrogens. Each carbon has how many hydrogen on it? Take a look. Look at each carbon. How many hydrogen? How many bonds can you see on each carbon? 2. How many bonds you don't see? 2. So each carbon has how many hydrogen? 2 hydrogens. So each carbon is a CH2. There are how many of those? 6, right? So 6 times 2 is what? 12. 12 carbons. Okay, this is C6H12. Okay, C6H12. Does it make sense, guys? So when you expand it, all you need to do what? Put carbon in there, put hydrogen in there, you could expand the structure. Like I said, practice. And after you expand this, you will see how ugly that is. That makes sense because we want neat, clear, clean organic structure representations. Okay? Next. Okay, next. Organic compounds. What time is it? Oh, we're almost here. Okay, we can stop here. That's fine. Let me stop the recording for